Hi everyone, thanks for attending this talk. I am Jalil Boukobza, professor at ENSTA Bretagne, a French state graduate and postgraduate and research institute in the Leipzig lab. It was supposed to be Mohamed, the first author, who presents this work. He left for job in industry and unfortunately couldn't do so. So I will do my best to try to explain his work. Our work is related to the design of a holistic scheduler for MapReduce jobs on ephemeral cloud resources. So here's the outline of this presentation. First, I will give some context and motivation for this work. Then I will introduce the problem statement. I will give some knowledge on MapReduce and some past work we did, and for which this one is an increment. Afterwards, I will describe the Salamander solution. I will then give some experimental results before concluding and give some perspectives. So scalability, elasticity, and reliability are important cloud features that made this computing paradigm indispensable in everyday life. These cloud features come at a price of over-provisioning resources to deal with workload peaks and node failures, and thus meet customer demands. Operating and managing such infrastructure is costly, resulting in an increase in TCO for cloud providers, and finally, low average resource utilization. It has been shown that this resource utilization is between 25 and 35% for the CPU and 40 to 50% for the RAM. As we can see here, if we consider only those two resources, CPU and memory, with the blue box being the CPU occupation and the memory usage, this is the used part in let's say cloud data center. Then we have the orange part, that is resources that are allocated but not used. The yellow part, which are reserved resources, and the green one, which is the free resources. We see here that there is a large proportion of resources that are unused, all except the blue part. And those can be better exploited. In order to improve cloud resource utilization and those reduce TCO, one can reclaim and make profit of the unused part. These are called ephemeral resources. That are volatile resources because it's imperative to be able to release them instantly in case their owner, that is, the customer who reserved those resources, needs them. At the Become Resource Institute, we investigated some more recent data center trace data sets to verify the proportion of unused resources. We can see in the table at the right-hand side 5 data centers with traces captured over 9 to 35 months for more than 51 metrics that we extracted on a 1-minute basis. The box plot on the left-hand side show only one metric, that is the CPU usage, and confirms the preceding numbers given. In fact, the mean CPU usage is about 15% over the trace period, and it is 75% of the time lower than 20% CPU usage. So this confirms the opportunity we have to better exploit data centers resources. One way to make profit of those large sets of unused resources is to deploy big data workloads at lower cost, since they require a considerable amount of computing resources and were democratized these last years. Most big data frameworks such as Hadoop were designed and developed with fault tolerance built in case of hardware failures. However, the reclaimed resources are volatile. That is, they may become unavailable at a much higher rate than the hardware failures. This means that the default Hadoop implementation is not really adapted to ephemeral resources as the running tasks on the preempted resources have to be rescheduled. Hadoop assumes that all resources are homogeneous, and thus the tasks are supposed to have the same execution time. However, this assumption doesn't hold in the case of heterogeneous resources. In fact, it has been shown that running Hadoop on such resources significantly degrades performance as resources may be over or under provisioned with regards to the executed jobs. So the problem we are trying to address here is how to design a scheduler for Hadoop jobs that run on heterogeneous and ephemeral resources while guaranteeing SLA. The issue we need to deal with are resource volatility and heterogeneity. Indeed, those properties provoke excessive task rescheduling, which degrades the overall performance, in particular for the run big data applications. They also provoke resource waste as many resources are used for futurely aborted tasks, which is useless. If the tasks are not well scheduled, they will be executed remotely, which increases the overall network traffic. And finally, if heterogeneity is not considered, running those big data jobs might interfere with regular collocated customer application, which causes SLA violations. A bit of background on Hadoop. Hadoop is an open source implementation of Google MapReduce to process large amounts of data and computation. Hadoop consists of two main components, a storage component called Hadoop Distributed File System, HDFS, and a processing component that is MapReduce programming module. In Hadoop, there is a master node managing a set of slave nodes. Each node has two layers that are MapReduce and HDFS. The master node consists of a job tracker and a name node. A slave node consists of a task tracker and a data node. The job tracker is responsible of scheduling tasks on task trackers and monitoring their execution. Each task tracker has configurable number of map and reuse slots, which limits the maximum number of simultaneous tasks in the node. User interact with the master node through the client node to submit computation in form of map and reduce functions. The data to be processed is split into chunks. By default, each chunk has a size of 128 megabytes and distributed uniformly to the data nodes. These chunks are replicated across the slave nodes with a certain replication factor, by default 3 replicas, but here in the example we show only 2 replicas. This is for fault tolerance. The Hadoop task scheduler favors data locality, is the process of moving tasks close to where the data chunk resides. Two types of task execution are possible, namely local and remote execution, which are differentiated according to the initial placement of the data. A task is considered as local, as the example here, when both task and data chunk process are initially placed on the same node. For instance, task C here. Otherwise, a task is said to be remote. For instance, task A here, where the task is not collocated with the data it needs to process. In a previous work, we have proposed a first framework to make it possible to run big data jobs on ephemeral cloud resources. It was called Cuckoo. As you might know, Cuckoo is a bird with a particular way for nesting eggs. In fact, it's a brood parasite. It lays eggs in the nest of other bird species for which they mimic the color. Hatch cuckoo chicks may push out host eggs out of the nest or be raised alongside the host's chicks. Common cuckoo chicks persuade their host parents to feed them by making a rapid begging call that sounds like a whole brood of host chicks. So, in a more technical way, the Cuckoo framework, this is a past work, of course, it relied on three main modules. First, a forecasting module. This module is used to predict future resource utilization in a cloud at the host level, considering multiple resource metrics. This module uses quantile regression to provide accurate predictions for reclaiming unused resources while still guaranteeing SLA. A data placement planner. This module is used to distribute data chunks across the cluster data nodes. It relies on the prediction from the forecasting builder to distribute data chunks using a weighted round-robin algorithm. And a QoS controller. This module guarantees that running Hadoop jobs do not interfere with the regular customer workload in order to ensure the SLA. The quality of service controller continuously monitors resource utilization to detect any interference. If it is the case, some corrective actions are triggered, such as killing a task. This preserves a certain amount of unused resource referred to as a safety margin to absorb workload variation or mispredictions. So let's move on to the solution proposed in this contribution. It's the Salamander solution. Our goal here is to build a framework that allows for efficient execution of Hadoop jobs on heterogeneous and ephemeral resources while guaranteeing SLA. The main role of our framework architecture as follows. We have a farmer. A farmer is a data center owner who seeks to reduce his TCO by offering unused resources to other customers. Then we have the customers. We can dissociate two types of customers. First, regular customers that buy and reserve stable resources, and ephemeral customers who want to process data-intensive application on a cloud at lower cost. Can do a parallel here with Spot instance. We have an operator who acts as the interface between the farmers and customers and aims at minimizing farmers' TCO by offering unused resources to customers with SLA requirements. So the framework is composed of four main modules. A forecasting module. This is the same as the one introduced in Cuckoo. In our solution, we use the predictions of this module in order to have a global overview of the amount of unused resources and their expected volatility. We have a holistic scheduler in this module, which is different, which is the new contribution with regards to Cuckoo. We implemented three solving strategies to schedule MapReduce jobs and tasks, using first constraint programming, second genetic algorithms, and third local search-based algorithms. Details about the implementation of each of the algorithms can be found in the paper. The scheduler here relies on the predictions from the forecasting builder and considers a safety margin for efficient execution of tasks, just like Cuckoo. But here we are placing mainly the tasks rather than the data like in Cuckoo. In Cuckoo, we mainly focus on data placement, but in Salamander, we focus on tasks placement using those algorithms, and then we will map the data on the same nodes that, that we have already mapped the tasks. So the data placement module simply uses the task scheduling of the holistic scheduler as a placement strategy to distribute data chunks across data nodes. Finally, we have the quality of service controller. This module is an improved version of the QoS controller introduced in Cuckoo. As explained earlier, the controller is a reactive mechanism that tries to eliminate interference between collocated workloads. While the previous version of the QoS controller relaunches tasks for any resource violation, such as CPU or RAM, the upgraded version does so only for incompressible resources. And for compressible resources, such as the CPU, we adjust the CPU frequency, we adjust the CPU proportion that we allocate to the tasks. We do not necessarily kill the tasks. Here the figure gives an overview of the Salamander architecture. It shows the different roles involved and the interactions between the aforementioned modules. First, the customer submit the MapReduce jobs using the client node. Then the job tracker sends a list of jobs to the holistic scheduler. Then from the forecasting, we get the prediction from the forecasting builder for the scheduling step. The module tries to schedule the submitted jobs in 24-hour time window, which is the forecasting horizon. This execution plan is then sent to the job tracker and the data placement module at the same time. Afterwards, a response is forwarded from the job tracker to the client node, indicating the schedulability of the jobs. Before the execution of any task, the client node requests the data chunks allocation from the name node in order to send them to the appropriate data node placed on reserved storage for temporarily hosting chunks and intermediate data. Finally, the job tracker assigns the tasks to the task tracker at a specific time using the generated scheduling. Periodically, the quality of service controller monitors the utilization of resources in order to resize the amount of allocated resources to the containers to minimize the interference. In fact, we have formalized the scheduling problem as an optimization problem that we solve using different approaches. Um, First, the amount of unused resources in a cloud infrastructure is calculated as follows. A, which is equal to C minus 1, C times 1 minus U plus S, where A here is the amount of unused resources for certain metric M in a given node K at time T. Ck is the capacity of a resource metric in node K. U represents the predicted percentage of resource usage in a node at a given time. This information comes from the forecasting builder. And S is the percentage of safety margin for a resource metric M. For instance, if uh, if the CPU occupation is 60%, that is U, and we apply a safety margin of 20%, that is S, we are left with 20% of unused resources, which is A. So here are the objective functions. The first function gives the total number of scheduled tasks and aims at maximizing it for a given time window. And the second function calculates the time at which the latest task finishes its execution. So minimizing this term means trying to have the smaller make span possible. And we have to fulfill three constraints. The first one is that all the scheduled tasks should be performed within a predefined time window. We need to bound the execution time. The second one is states that the job has to be either fully scheduled or rejected while respecting the dependencies according to the MapReduce paradigm. And the third one stipulates that tasks can be scheduled on nodes only when there are sufficient available resources for the whole execution to avoid SLA violations. So for the quality of service controller, which is reactive mechanisms, so as we previously said, we dissociate the two options, whether we consider the resource to be compressible, such as CPU. So if the resource is compressible, MapReduce task execution is slowed down. And in case of incompressible resources, that is a RAM, memory, MapReduce tasks are killed in case of violations, like in Cuckoo. This difference between compressible and incompressible resources is particularly relevant when using the forecasting builder. Indeed, CPU predictions generate more errors than memories. Thus, as compared to Cuckoo, much less tasks are killed because of CPU misprediction. The proposed scheduler in the previous module allows to determine the starting time of a task, but most importantly, in which node it is executed. This module uses a task scheduling generated by the holistic scheduler as a placement strategy to distribute data chunks across nodes. This module uses the task scheduling generated by the holistic scheduler as a placement strategy to distribute data and keep them with the task with the tasks to be executed. So for the experimental validation, we considered three resource questions. Only two of them will be discussed here for this presentation. The first one was the overall performance of the contribution. We compared the three algorithms implemented in Salamander with Cuckoo, and we have evaluated the job execution time and the proportion of remote and relaunch tasks. And the second research question is how do the solving strategies scale with the number of jobs? We compared here the three strategies of Salamander, and the metrics used are solving time and quality of scheduling. For the third research question, which is dedicated to the quality of service controller we implemented in Salamander, we can find details on the paper. We have experimented with a 70-day in production dataset from 3 data centers, and we have used the CCGrid simulation scheduler. For the first research question, the figure shows the job execution time with 128 and 256 megabyte chunk sizes. A first observation we can draw is that the three strategies of Salamander behave similarly with a slight difference of less than 1%. The solving strategy generated comparable scheduling of tasks. With 128 chunks, the three solving strategies outperformed Cuckoo with faster execution time of 9%, 11, and 9% for the three data centers. With 256 megabyte chunks, Salamander improves the median job execution time by 30%, 5.2 for PC2 and 47% for the last dataset. We notice that the lower the number of available nodes in the data center, the higher the improvement. Contrary to 128 megabyte chunks, in fact, the longer the execution time, the more tasks are prone to prediction errors. And in this case, Cuckoo is more prone to task failure solo because it's solely scheduled on CPU occupation basis. The left table here shows the percentage of relaunch tasks with minimum, maximum, and median and 98th percentile values. We show only the results for the university with 256 megabyte chunks and 5% of safety margin. That is the worst case for Salamander. We observe that Salamander reduced considerably the percentage of relaunch tasks compared to Cuckoo. The high percentage observed for Cuckoo is due to the fixed number of slots for map and reduced tasks. In contrast, Salamander's task scheduling dynamically resizes the number of slots according to the prediction, which helps to have less SLA violations. The right table represents the percentage of remote task execution for Salamander and Cuckoo. We observe that Salamander does not execute remote tasks, while Cuckoo executes about 10% of tasks remotely. Such results are obtained since Salamander data placement strategy places chunks exactly where tasks are about to be executed, which reduces data transfers between nodes. In this experiment, Salamander improved the job execution time by up to 47% and on average by 18% compared to Cuckoo. It also reduced considerably both relaunch and remote tasks as far as node failure doesn't occur. For the second research question, as we can see here, we compared the scalability and quality of Salamander solving strategies. The first figure on the right-hand side depicts the results of the solving time of the three strategies for PC1. The figure on the left represents the scheduling quality of the strategies. In the right figure, we observe that both GA and LS have almost similar solving time, which is linear. However, the solving time of CP is exponential, with difference of up to a factor 6 for 2,500 tasks compared to GA and LS. Furthermore, we observe in the left figure that while CP took much longer time in solving, it only gave a better scheduling quality of around 4%, 4 to 10% compared to GA and LS. This means that CP scales up poorly. As for the RAM usage, CP used up to 2 gigabytes, genetic algorithm up to 1.8 gigabytes, while LS used up to 1.3 gigabytes. In order to choose the appropriate strategy, one must consider the problem size, the solving time, and the amount of resources available. For our case, CP can be used for problems with less than 1,500 tasks since it gave the optimal scheduling in reasonable time. However, for large number of tasks, one may use GALS since they have similar quality. That being said, ALS can be used in case of memory footprint issues. So to conclude, um, the idea here came from the observation that large proportion of cloud data centers are poorly used, so our contribution consists in exploiting those unused resources in order to run big data jobs at lower cost while still guaranteeing a certain level of SLA. We designed Salamander, a framework to reschedule big data jobs on ephemeral and heterogeneous cloud resources. We designed three solving solutions for such a sake. We used constraint programming, local search, and genetic algorithm. Our strategy proved to enhance the previously designed Cuckoo by 20% on execution times, as it generates much less interrupted, thus relaunch tasks. So for future work, we will try to integrate other metrics to the scheduling policy, such as storage and network. Also, data replication has been considered in our work. Implementing it would enhance the performance and make it possible to evaluate the impact of node failures. If prediction error occurs, Salamander simply drops the tasks and reprogram it later. It would be interesting to reschedule the task in a more relevant way, for instance, based on predictions. And when the forecasting builder overestimates the resource utilization, there is still a large proportion of resources that remain unused. We have designed, since last year, a novel strategy that uses reinforcement learning to dynamically adjust the safety margin. Results can be found in the paper you have here. So this concludes my talk. Thank you for your attention.